Here we go. What is this, 4.3, number 5? All right, so 4.3, number 5. You've got two blocks, right? Was the little one in front? Was it 25 kilograms and then 50 kilograms? Is that right? Good. All right, and you're given your coefficients of friction. You're told that the coefficient of static friction is 0.3, and your coefficient of kinetic friction is 0.2. Is that right? 0.15. Okay. I'm sorry, I gave away the copy that I had sitting up here. All right. And then the problem tells us that Roy pushes the system with a force of 300 newtons, yes? So, the first thing you want to do is look at the full system, all right? So, for my system, what forces are there? So, always start with gravity. So to find my gravity, what am I going to use for my mass? 75 times 9.8 gives you 735 newtons, right? Everybody good up to there? Okay, your normal force is also going to be 735 newtons. At this point, I can use my coefficients of friction to find my forces of friction, right? So static friction max ends up being 735 times 0.3. 735 times 0.3, so you get 220.5. So now what? Does it move?
Yes.
Yeah, it moves because the force from Roy was 300 newtons, right? Everybody good up to there? Okay, so this isn't enough friction, so let's find our kinetic friction. That ends up being 110.25. Am I going too quick? Okay. So put that in the drawing. Force of friction, kinetic, 110.25 newtons. So now I can find the net force on my system. It's going to be 300 minus 110.25. Which gives you 89.75, is that right?
Yeah.
Newtons. So there's the net force on the system.
180.
Sorry?
180.
Oh, 180. Thank you. Thanks. Everybody good? Okay, so what now? Find the acceleration. So the acceleration of the system is net force over mass. Our mass is 75 kilograms. So divide this out and you get 2.53. Thank you. All right. AJ, good?
Yeah.
You sure?
Yeah.
Question? Are you going to tell me you did it different?
Yeah, I still got something.
Okay, so you must be doing something right a different way.
I don't know what I'm doing right.
If you can't explain it, I can't explain it. I'll look at it, okay? All right, is everybody good up to here? All right, cool. So that's always step one. Look at the system, find the acceleration. Everybody's good with that, yes? All right, so now what the question says, I don't remember the exact wording, but it says find the forces the boxes exert on each other, right? Is that how it's worded?
Yeah.
Okay, so here's the deal, you guys. Why is the bigger box moving? Let me ask you a different question. What's Roy doing? Pushing which box? The little one, right? So the little box moves because Roy pushes it. But Roy's not touching the big box. So why does the big box move?
Force of box A from Roy.
Good. The little box is going to push it, right? It's this. You've got a little box and a big box, right? Roy pushes the little box and the big box moves, right? So why is the big box moving? Oh, because the little box is pushing it, right? So to find the force that the boxes exert on each other, what it's asking you is find either the force of the big box pushing the little box, or equivalently, the force of the little box pushing the big box. Why are they equal? Third law. Very good. Cool? So to find that force, what should I do? New system, right? And I need to choose a system for which one of those forces is external, right? So we got to pick one of the individual boxes, yes? It doesn't matter which one you pick. There's usually an easier choice. I think choice B is easier. All right, so let's do that. So let's now take a look at box B. So what do we know about box B? Well, let's see. Box B was 50 kilograms, right? Forces on it, gravity, normal force, force of Roy, question mark?
Wait, no, force of.
No force of Roy. Remember, Roy is pushing the little box, not the big box. Okay? So what did we decide? So if this is box B, what did we decide was pushing it forward? The force of box A. So this is the force on box B by box A. Is it 300 newtons? No. Because this is a little bit sloppy, but some of the 300 newtons got used by the little box. And box B sort of gets the leftovers. Okay? Not exactly, but... So we don't know that force. That's what we're trying to find. Good. All right, so there is one other force, though, that I need on my drawing. What do I need? Friction. 110, right?
No.
No, why not?
Because that's exerted on box A, right?
Okay, so I did like two separate ways.
Hang on 1 second. I want to resolve the friction issue before
Why
we
did I
get...
get into this?
Oh, okay. Okay, go ahead. I'm sorry.
Well, because box A, did you have? Oh, because it has a different mass. It's not going to be 110. You're going to have to recalculate it.
Exactly so. Yeah, remember, you guys, friction is normal force times coefficient. My normal force has changed. It's only 490 now, right? Follow? So I got to recalculate my kinetic friction. So it's my coefficient, 0.15, times 490, right? And that gives you a number which I don't remember off the top of my head. And I sat down my calculator because I'm dumb. 73.5. 73.5. Thank you. I agree with that. Okay, good. And the friction's going to go to the left, right? Everybody good up to there? Okay, so I know one other thing about box B. Yeah, we know the acceleration, right? So that feels useful. Oh, darn it. So my acceleration is 2.53 meters a second squared, so I should automatically find my net force. So mass is 50, acceleration is 2.53, multiply it out, and you get 126.5 newtons. Good? Any problems? You guys follow the process or no? Okay. Yeah, question?
Okay, so originally I did not include force of friction kinetic kinetic friction, but then I used 4 meters a second. 4 meters a second squared.
That's what the acceleration would be with no friction.
Yeah, but I still get
You still get the same 200 newtons, which
Yeah.
is weird. That's question C.
yeah.
Are you sure you're not looking at question C?
I guess
No.
not.
Okay. Yeah, it turns out it doesn't matter. Friction or no friction, they still push each other with the same force. Okay, everybody good up to here? All right, so now what's my last step for box B? We're almost done. What do you got, AJ? Why don't you take it? Yeah, I mean, basically, we got to figure out what this has to be to get my net force up to 126, right? So net force is the force on B from A plus the force of friction, right? So 126.5 equals the force on B from A minus 73.5. Add to both sides, and you get 200 newtons. Good or no? Wyatt, you good?
Yeah.
Everybody good? Had you not recalculated the friction? Is that what messed you up?
Yeah, I just like didn't understand what the question was asking.
Gotcha. All right, everybody good? Yeah, shoot.
Over C as well.
Yep. All right, we good? Okay. All right. I would like you to try to get in the habit of checking your answer. So how can I check? Look at the other box. Look at box A, right? So let's do that real quick. So what do we know about box A? We know that it's 25 kilograms, which means the force of gravity is negative 245. We know the normal force is going to cancel that out. I know the force from Roy is 300 newtons. I just figured out that A pushes B with 200 newtons. So that means that B pushes A with negative 200 newtons. Good. I can find my new kinetic friction. It's going to end up being 36.75. Good or no? All right, so how do I use all that garbage to check it? What do you say? 245. Oh, right. You mean you're checking this? I'm sorry. I meant, is that what you were saying? Right. So what I meant was, so we already finished the problem, right? We already figured out our acceleration and our force that the two objects are exerting on each other. So we're done with the problem. So everything that I've written over here in green is extra. What's the point? What am I trying to see? Well, I want to ensure that with these forces that I've calculated, that I get the same acceleration. Do you see what I'm saying, Sarah? Okay, so now, just one last step, let's see if this gives us the right acceleration. So acceleration is net force over mass. Well, our net force is 300 minus 200 minus 36.75. Our mass is 25 kilograms. Divide it out, and you get whatever the acceleration was, 2.53 meters a second squared, which makes us happy, because that's what we were supposed to get. Good? Yeah?
Why did you say that it was easier to do than A?
Why did I say what?
You said you want to check it with A, but you did B first. Like, why is B the easier?
Oh, just because there's less forces on it. There are 3 forces on this block, right? Roy, friction, and the other block. And there are only 2 forces on this one, because you don't have to worry about Roy's force. It doesn't really matter, you know, whatever. Good? Yeah, Caleb.
Explain the kinetic friction thing.
Yeah, so in our original problem, like when we looked at the original system, the question, if you didn't hear it, was to explain the kinetic friction again. So in the original problem, when we were looking at the whole system, our normal force was 735, right? And so that determined my force of kinetic friction. Cool?
Yep.
Now, when I look at the individual boxes, you've got a different normal force, and therefore a different force of friction.
Oh, okay.
So I had to recalculate the friction by multiplying by the coefficient of friction again.
Yeah. Okay.
Follow?
Makes sense, yeah.
Everybody good? Yeah.
For the review, for number 1, like you were just assuming that we're pushing to the right?
Sure. Yeah. If you want to push to the left, it doesn't matter.
Okay, cool.
Okay, so real quick, you guys, if you, the bell's going to ring in a minute here, so I think we're out of time. So reviews due Monday. AJ, you asked about Part C. Part C is the exact same thing, but with no friction. And weirdly, you get a bigger acceleration because there's no friction, but they still exert 200 newtons of force on each other. Okay, just like because of physics, but it's a neat result. It's not obvious. Okay? Yeah, yeah. All right. Steer the one